Hey, today we're going to be talking about equivalent resistance in a parallel circuit. The previous Google form and video were on equivalent resistance in a series circuit. And just to review, series circuits, you just add all the resistances up, and that gives you the total resistance of the circuit. Parallel circuits work a little bit differently, and that's what we're going to talk about today. So just to review, parallel circuit. What the heck is a parallel circuit? Well, parallel circuit means you have multiple complete paths for the electrons. We know that if we take a light bulb out of a parallel circuit, the other bulbs should stay on. In the example I have to the left, I just have some resistors. If R2 is a light bulb and it went out, R1 would still light, and vice versa. So that's what that is. What's the same about all the resistors, whether they be light bulbs or motors or buzzers or what have you? What would be the same about them? Well, they would get the same voltage from the battery. So if this is a 9-volt battery, R1 would get all the voltage, all 9 volts, and R2 would also get all 9 volts. In one of our previous videos, I made the analogy of the electrons having backpacks full of energy. When the electrons leave the battery, no matter if they choose to take path 1 or path 2, they all have full backpacks. So the electrons that march up and go through R1 are carrying full backpacks, 9 volts, and the electrons that march through R2 are also carrying full backpacks of 9 volts. So the voltage for every element is the same, regardless of how many branches there are or the resistances of those resistors. They all get full charge. What's different about each element? Yes, R1 and R2 could have different resistances, and that is definitely something. The other thing that's different is that they get different currents. The current splits. So whatever current comes out of the battery is going to actually separate into 2 branches or 3 branches or more branches, depending on how many parallel circuits you have. So they are not going to get the full current from the battery, and they actually might get different percentages of that current. So that's going to be something that's different. So what happens to the resistance in a circuit like this? In a series circuit, we know that the more resistors you put in the way, the slower the electrons go, which means the overall resistance of the circuit would increase. Parallel is different. The more paths you put in for the electrons, the more choices they have, and the faster they can go, which means there is less resistance, there's less obstacles in their way. If they can all go different ways, they're going to get where they're going faster, so there are fewer obstacles in their way. So the more resistors you put in a parallel circuit, the less overall resistance you get. More branches mean the current can split more, which means the electrons can move faster. Okay, so equivalent resistance. Series circuit, yet again, we just add them up. The total resistance is R1 plus R2 plus R3 plus however many R's you have. And the number gets bigger and bigger and bigger the more resistors you add. Equivalent resistance is different. The more resistors you add, the smaller your number should get overall, which means your equation looks like this. The inverse of your total resistance equals all the inverses added together. Okay, so what does that look like in an actual problem? Well, let's take a look. 1 over RT equals 1 over R1 plus 1 over R2. So 1 over RT equals 1 over 1, because there's resistor 1, sorry about that big smear, plus 1 over R2, which is 2, which again, here's 2. All right, so 1 over RT equals 1 plus 1/2. Okay, that equals, which equals 3 over 2, if we keep it in fractions. You can put it in decimals, that's fine, it'd be 1.5. The important thing to remember, though, is this is an inverse. So that means in order to make this RT, you have to actually flip it. And if you flip one side, you have to flip the other side. So if 1 over RT is 3/2, that means RT is 2 over 3. Okay, that makes, hopefully that makes sense. I'll go through that one more time. If the inverse of RT is 3/2, that means RT has to be 2/3, because when you take the inverse of this, you would flip this side over and get 3/2. It's a little complicated, all right, just a little bit complicated. So how do we use this to figure out some stuff about the circuit? How can we figure out the current in the circuit? How can we figure out the current in each branch? And that's what we're going to take a look at now. We're going to go ahead and use Ohm's law to do that. So let me come back over here. We know Ohm's law is V equals IR. So how do you use it? Well, first you find the equivalent resistance, which we did. It's 2/3. I'm going to actually go ahead and erase some stuff here. So hold on 1 second. Eraser. Make it big. Erase this. Sorry about this. I probably should have paused the video at this point, but you know what? Live and learn. Okay, so let's put our pen back. All right, so we know the equivalent resistance, our total, we figured it out, was 2/3. I did not ask before, and I should have. 2/3 what? What are our units? Resistance is measured in ohms, which is, we use the Greek letter omega for ohms. So we know the total resistance of this circuit is 2/3 of an ohm. So we can take out resistor 1 and resistor 2. We can replace them with one single resistor that has a resistance of 2/3. Earlier we said the resistance should go down the more resistors you add. So we started with 1, and then we had added another resistor that was 2, but you can see the overall resistance is much, much smaller. Your total resistance in a parallel circuit should always be smaller than your smallest resistor. Okay, I'll say that one more time. Your total resistance in a parallel circuit should always be smaller than your smallest resistor. So our smallest resistor is 1. 2/3 is definitely smaller than 1, so we're in good shape. So how do we figure out the current flowing through the circuit? Well, we use V equals IR. Our voltage is still 9. It's a 9-volt battery. I, and we know this should be 2/3. Okay, so so 13.5. Yes. All right, so when I do out the math on the calculator, I get 13.5 amps. So 13.5 amps. Dot, there we go. So 13.5 amps. So this circuit has 13.5 amps flowing through it. We know that when those 13.5 amps get here, they are going to split. Some of them are going to go this way, and some of them are going to go that way. So how do we use this? How do we figure out which is which? Well, we know that all the elements get the maximum voltage. So we can figure out how much current goes through R1 and how much current goes through R2. I'm going to erase the board, but I'm going to be smart and pause my recording for a second. So hang in there. And I'm back with a clean board. So we left off. We can use the fact that all the elements get the maximum voltage to figure out how much of that 13.5 amps each of them gets, which means we have to do V equals IR twice. So we have V equals IR. So 9 volts current for the resistor 1, which is 1 ohms. That means resistor 1 gets 9 amps of the voltage. Let's do this again for resistor 2. 9 equals I times 2, which means 4.5 amps equals I. Okay, so earlier we figured out that the current coming out of the battery was 13.5. This means that current in resistor 1 plus current in resistor 2 should add up to 13.5 amps. And if you get your calculator out, 9 plus 4.5, lo and behold, equals 13.5 amps. So 13.5 amps comes out of the battery. 9 of those amps go up here to resistor 1. The other 4.5 of the amps go here to resistor 2. So as I said earlier, they don't always split evenly, because if the only reason they would split evenly is if they had the same resistance. So if one of them has more or less resistance, they're going to get more or less of the current. All right, so just to recap, for Ohm's law, equivalent resistance will find the total current in the circuit. Knowing that all the elements get the maximum voltage, you can find the current for each resistor, and then you just need to make sure that they add up to the total current. So we used the 2/3 to figure out that the current was 13.5. We used each individual resistance to find the individual currents, and then they should add up to 13.5, which they do. Okay, as always, if you have any questions on something you watched, you're not sure what the heck I'm talking about, pause the video, ask me, I'll give it a listen and try to explain what I'm talking about. Otherwise, there are some questions on the Google form that this is contained on. And you're going to go ahead and answer those questions to the best of your ability. All right, I hope this was helpful. And again, ask questions in class if you are stuck. Have a good one.